Cugno, like in Pigno.
Oh, Cugno, okay. So Gabriele Cugno is going to talk to us now from University of Zurich, yet another planetary mass companion with carbonaceous composition.
Indeed. Does it work? Yes, thanks. Yes, my name is Gabriele Cugno. I'm from the University of Zurich. I'm a postdoc there. And today I hope to keep convincing you after these two talks that CPDs are really important. And this is, in my opinion, for two main reasons. Number one, they set the stage for the subsequent evolutionary pattern of the planet through accretion processes. And number two, they really provide the material for both the planet atmosphere, but also for the moons. And this is really interesting when we think about solar system moons and habitability potentially beyond Earth. So ideally, we want to study a CPD like this one. This is PD70C. It's the only CPD that we have imaged in a millimeter where we are really probing the pebbles from the dust from the CPD. Unfortunately, this is really difficult because in order to probe the main tracers for the gas and the dust of CPDs, we need to go in the mid-infrared. And ideally, of course, when we think about mid-infrared, we think about JWST. This is a plot that shows what JWST can do in terms of gas analysis. So basically, once you remove the continuum from any point source, you are left with a bunch of features, in particular, what they look like emission lines. And these are all emissions lines coming from gas in the disk. We can also look at the dust in the mid-infrared, sorry. And we do it mostly through silicate features. So when the dust is small enough, it produces this type of features in the spectrum. And when the dust grows, we really see this feature disappearing with the growing dust. And so we are directly probing the dust in the disk, the dust growth in the disk. Additionally, we have a bunch of peaks in there that we can use to infer chemical composition and crystallinity of the dust. And finally, the overall trend and slope of the mid-infrared spectrum tells us something about settling and flaring and overall structure of the disk. The problem is, if we go back to our friend PD70C, is that this is the typical pixel grid of MRS at 12 micron. And if we talk about angular resolution, this is the 1 lambda over d circle. So we have A, we have planet C with the CPD, and even B is not detected in ALMA yet, but it's in there. And so, of course, it's going to be really hard to be able to distinguish and disentangle the signal from the CPD from the signal from the planet, or probably impossible. So what we do, we turn to what we call analogs or planetary mass companions that have a CPD. So these objects are usually farther or more distant from the star, so it's a bit easier to detect. Easier doesn't mean easy, but it's easier. And additionally, they are usually a bit more massive. And again, this makes them brighter and easier to detect. So with the MRS, we managed to detect a few of them so far, or a few of them have already been published. One of them is GQLoop, where we applied really classical RDI, reference differential imaging, in order to detect the companion. So we built a library of references, we removed the PSF, and we revealed GQLoop-B. We were also able to get the full spectrum up to 12 micron, and the advantage here is that we can obtain and retain the continuum. And so this is really good when we want to observe dust features and the overall spectrum or SCD of the companion. Another option is to use what was discussed this morning, which is spectral cross-correlation. So basically here, instead of looking at the continuum or removing the PSF, we just look for the features that we expect in something like CT-Cha-B. What do we expect in CT-Cha-B? Well, for the cross-correlation model, we just used a spectrum from another object observed by MRS with a disk that has a similar spectral type. So this was our first idea, and it worked really well, so we stick with it. Concretely, this means that we just used an object that has a lot of hydrocarbons in the spectrum. So this is once you extract the spectrum of CT-Cha-B, and you see that we were able to detect a bunch of molecules. Now, in total, we detected 7 molecules, and all of them were containing some carbon atoms. Oxygen is only present in form of CO2, and we also detected one isotopolog, 13CCH2, which really means that this disk overall is very carbon rich. We also ran the cross-correlation on individual molecules, just to double check that we were doing everything correctly. And indeed, you see that when you take just for example, the HCN model, there is one single signal, exactly the position of the companion that pops up. When you do the same with H2O, with water, you get something different. There is a pattern in there, a silhouette, that really looks like the one from the star. And the reason is that the stellar spectrum, or the spectrum of the disk surrounding the star, contains some water, but does not contain any carbon-bearing molecules. So here you see the wavelength regions where we have signal from C2H2, HCN, benzene, and CO2, and we don't detect them. So this is also why spectral cross-correlation was so efficient. The two disks are completely different. It's the same when we try to observe an atmosphere and we cross-correlate with water model because the star doesn't have any water in the atmosphere. Now, the disk around the star is oxygen-rich. The disk around the planet is carbon-rich. And this is really interesting because it means that in terms of evolution, these two objects probably formed from the same cloud, from the same material, roughly at the same time, 1 to 2 million years. But now they look so different. And so it means that there must be some evolutionary process at the disk level that makes sure that this is possible in just 1 or 2 million years, which is the age of the system. This plot shows the C2H2 over H2O ratio, which is a proxy for the C2O ratio, as a function of the luminosity of the central object. In black, you see a bunch of objects observed by the MINDS survey, and we are including some objects from a Cycle 2 program led by Sierra Grant on brown dwarfs and very low mass stars. And you see that when taken individually, both CTCHA and CTCHB fit very well in this story. Right? There is a trend. C2O increases when you go to lower masses or lower luminosities, and both CTCHA is consistent with T-Tauri stars, and CTCHB is consistent with very low mass stars and brown dwarfs. We are starting to enter the new regime of CPD and planetary mass objects, and this is done even more when we include the measurement from Mathilde Malin on Delorme ABB. Now, the flux here, it's an upper limit, right? So it must be above that level. The limit is not so high, and the reason is the planet or the CPD signal is really faint, but it's consistent with the full story. Now, the question is, can we really populate this area of CPD, of planetary mass objects? And we think we can. This is the full list of available CPDs that could be observed by MRS, so where we have enough separation, the contrast is good enough, the disk is bright enough, and so everything is ready for us to just observe the disk, get the dust information, get the gas information. One data set, I was hoping to show something today, but unfortunately, in the end, was scheduled for Friday, so the conference was organized a week too early. But yeah, so once every team did, so the green targets were already observed by different teams, and of course every team will publish their results on their own. But then in the end, we can really try to have a look at this sample as an entire population. And I think it's really an interesting sample because these are 9 targets in total, and 5 of them are really young, 2 of them are intermediate age, and 2 of them are relatively old. And so when we have all of them together, we can really try to build a coherent picture of dust and gas evolution in CPDs and how these 2 elements behave and coexist around these objects. With this, I'm ready to leave you with my conclusions. So I think we are entering an era of high contrast imaging or high contrast spectroscopy with the MRS. And today we focused on CPDs, but actually this is valid also for planets. I know there are several programs that are targeting gas giants in general. We have a dichotomy between CTCHB and A spectra that we are trying to understand. It has to do something with evolution. And by the end of cycle 4, we will have the complete, all the observations of the complete sample of CPDs taken with MRS. In terms of challenges, I think we want at some point to find a way to retain both the continuum and the full MRS resolution without sacrificing it. Fringes, in terms of PSF subtraction, remained, in my opinion, the main challenge. And if someone is interested, I would be happy to talk about it. And finally, I think one open point is this is what we can do, and this is what we will be able to do also in terms of, at least for the gas, also in the METIS era. METIS, the gas features are in a region of the spectrum that will not be accessible even by METIS. And so this is really the best opportunity to study what happens in terms of gas in these objects, and then we have to find a way to translate this into objects like PD70, where clearly there are some differences, right? These objects are embedded in the circumstellar disk, are still interacting with the circumstellar disk. So physically, there are some differences, and we have to find a way to translate and have these two type of targets communicate with each other. Thank you.
Okay, thank you. Do we have any questions in the room here? Looked like there was one in the back coming up here.
Hi, Gabriele. Great talk. I'm curious, like, how close are you to converting, like, carbon-rich or oxygen-rich to, like, values? Like,
sorry, I didn't hear you well.
Like, you get that you found that the CPD around the companion is carbon-rich, while around the disk around the host star is oxygen-rich.
Yeah.
Like, how close are we to converting those to, like, abundance values or something?
Okay. So this is a bit more tricky. I think, so first of all, this observation were taken in the first month of GWST, and I think it's fair to say that we were all learning and understanding what was happening. And I'm saying this because if we were now to take the same exact observation with the same exact exposure time, we could aim at a factor of 6, 7 better SNR. Just by knowing how the detector works, knowing how the PSF subtraction works, knowing a bunch of other stuff. In terms of composition, here we are. So for A, I think we have a good handle, a good understanding of the composition. The fit really gives good results. Could be better if we could handle better the fringes, but at the moment it's not too bad. In terms of the companion, on the other hand, this is why we are not providing a number in terms of, for example, C2O ratio. The red lines in these plots show the 1 sigma uncertainties. And you see that they are quite huge. Even for something like the C2H2, which is really strong, right? It could be something cold and around 10 to the 19 in column density, or something 10 to the minus 14, but hotter. So it's really not doable at the moment to quantify C2O ratio or abundances. But for the upcoming observations, I think it will be possible. We aim very high in terms of signal to noise.
Hi, Gabriele. Really awesome talk and exciting to see all of your upcoming objects too. I was really struck by the plot where you show the ratio of acetylene to water as a function of the mass of the objects.
Yeah.
And I was curious if what really strikes me here is the dispersion that you see at any given mass. So do you think that we're starting to see effects of like evolutionary state here, or what is driving like the variation that we're seeing?
It's a good question. And my background is not in disk, so I'm not the perfect person to describe this. There are several scenarios that we are trying to explore. One of them is just about optical depth. So when you go to lower mass stars or lower mass objects, the dust is more settled, and so you can probe deeper into the disk. And so all of a sudden you see more or a higher column of these hydrocarbons. Another option is related to evolution. If your low mass objects usually have the pebbles are expected to drift inwards faster. And so at some point you consume all your water immediately because the water ice line is super close, right? So you bring in all the water while the hydrocarbons sublimate much earlier and so stay in the disk in the gaseous phase much longer. And this is why at 1, 2, 3, 4 million years when we observe them, we see so much more hydrocarbons than water just because the water is already gone. These are the two main scenarios at the moment. There are a few other options. But yeah, I think we're working on it, especially theoreticians that are really trying to explore these options. Yeah.
Thank you.
Okay, thanks, Gabriele. That's all the time we have.